Okay, folks, so today we are going to continue on the discussion we started on risk preferences. We started by motivating why we want to study risk preferences. The reason is that it turns out that most of the decisions that we make every day, and we gave a bunch of examples of this, are all decisions that are made under uncertainty. What that means is when we are making the decisions, we aren't really sure what the outcomes are going to be. And in such situations, when we aren't sure what the outcomes are going to be, we are facing a risky situation, so it matters how we deal with that risk. And the goal of studying risk preferences is to try and somehow figure out how to deal with these risky situations. We studied three concepts to talk about how we can think about decisions made under risk. The first concept was that of expected value. And the idea of expected value was, if I have a stock option or if I have some kind of a risky option, then how much do I get on average? That was the idea of expected value. It turns out that expected value doesn't really capture everything that we would like to capture in a risky situation. This is what made us think about a second concept, and that second concept was variance. And the idea of variance was that how much do the outcomes vary on average? So it might be that the outcomes are always close to each other and they don't vary as much, versus it might be a situation where the outcomes do vary quite a lot. So you might get plus 1,000 or minus 1,000, and you might worry about how far apart those two outcomes are, and that is captured by variance. Then we talked about the third concept, and what we said is economists actually use neither expected value nor variance, but instead they use this third concept of expected utility to capture the idea of decision making under uncertainty. Two things separated expected utility from expected value or variance. Firstly, when we talk about expected utility, we must start by talking about what is the utility function. Second, when we talk about expected utility, the initial wealth always matters. I needed to tell you what the initial wealth was for a person for you to do any kind of expected utility calculation. I want you to remember those two differences very carefully. Next, what we started talking about is, could I ask you a question, and could I get some measure of risk preference from you by asking you these questions? In particular, we saw this question being asked. We asked exactly this question, where what it asked was, you have two options. One option was a coin is tossed. You could get either $10 or $0 with equal chance. That was option one. And option two was you could get X dollars for certain. And the question I asked you was, what is the amount of X for certain that will make you indifferent to the lottery? And the reason I said, like what I motivated with this question was, this wasn't just one question, this was rather a question that motivates a definition of certainty equivalent. As you can see, this question is titled Finding Certainty Equivalent. So we're going to see three definitions which have all been motivated in the last class, but I want you to remember those three definitions, so I'm also going to write them down. So we talked about a certainty equivalent, and the certainty equivalent was the idea that if I give you a lottery, so I give you some lottery, and then I ask you what's the amount of X for certain, that makes you indifferent. And whatever is the X that you would give me, that I would call the certainty equivalent of that lottery. And in particular, on the quiz question that I was showing you that we did in the last class, we asked you to give you your own X. So clearly, each person might come up with a different X. So we asked you what would be your favorite X that would make you indifferent to a particular lottery. And the example that we had in terms of lottery was the following one. We gave you $10 and $0 with equal chances, 50-50. Okay. So that's the definition of certainty equivalent. That's going to turn out to be important for the class, so I want you to remember this definition of certainty equivalent. Now, today, the room name we are going to use is this one. just to make sure everyone can see it. This is the room name. It's Risk 100 BB2. It's the second class, so that's the last two at the end of the Risk 100 BB. Yeah, that's the room name. I want you to log in with your student ID and then the room name, and then we want to talk a little bit more about some of these concepts. In particular, I want you to attempt this question. It's another question that you should see on your screen once you log in. I just have the room name up here for anyone who came in late. And then once you log in, you should see a question on your screen. This question is going to ask you, which of the two options do you prefer? Would you rather take an equal odds of $10 and $0, or would you choose $5 for certain? It's a very similar kind of question. I want you to answer the question, and then I'm going to tell you why that question is important when we study risk preferences. For anyone who came in late, this is the room name that we're using. I would ask you to log in with this room name and attempt the question that you see on the screen. It's a question which has nothing to do with being right or wrong, but it has everything to do with your preferences. And when it comes to preferences, economists generally aren't people who would say that this preference is right and this preference is wrong. Preferences are just preferences. They are who you are. I'm just trying to understand who you are in terms of answering this question. Now, why is this question interesting? This brings us to the next definition that I want you to always remember. And the next definition is, I'm going to write it down. Think of a choice being made between a lottery and the expected value of that lottery for certain. Okay, think of the choice between a lottery and the expected value of that lottery for certain. For example, in this question that you just saw, I gave you the lottery which was going to give you $10 or $0 with equal chance, 0.5 probabilities, versus the expected value of this lottery for certain. What's the expected value of this lottery? Where you get 10 or 0 with equal chance? Yes? Yes. Right, so this is what the question asks you for. It asks you to compare, if I were to give you the choice between this lottery and $5 for certain, how would you choose? And here is the definition part. I can show you how people answer this question, but before we do that, I want to talk about the definition and then I can reveal the answers to you. The definition is that there would be some people who would prefer the expected value for certain over the lottery. There would be some people who would say that they prefer the lottery over the expected value. And there will be others, as you will see once I show you the screen, who would say that they kind of like the lottery or the expected value of the lottery equally. They don't care which one they get. They're indifferent between those two options. Now think about what these choices mean. What is common among these choices, this choice, the lottery and the expected value, is that they both deliver the same amount of money on average. In particular, in the example, they're both delivering $5 on average. This is just by definition. So they're both delivering the same amount of money. The main difference is, in one of the delivery systems, there is no risk in that delivery. You always get $5 guaranteed. Whereas in the other one, you're getting $5 on average, true, but it comes with risk. Because you might get 10 or you might get 0. So these are, in a way, right, a delivery system of money. But this one has no risk in it versus the lottery has risk in it. But they're delivering the same amount of money. So when a person says that, look, given the amount of money being delivered this is the same, I would rather take the expected value than the lottery, they're saying that I don't like the risk in the lottery. They are revealing their aversion towards the risk. So these are the folks that we are going to classify as risk averse. Similarly, there would be people who would look at these two options, and even though they are delivering the same amount of money, would choose the lottery. And it would look as if their choices reveal that they would rather have that on average $5 be delivered through a mode of risk. And that means they are revealing in some way a preference for the risk. So these are the folks that we are going to classify as risk loving. And then there is this third category who say that they wouldn't care either way. They think that both of them are exactly the same. And these are the folks that we are going to call risk neutral. So what are we defining? We are defining risk attitudes here. Risk attitudes means that once someone sees that there is a risky situation, what is their attitude towards that risk? And we are classifying people, but we are classifying them based on a very simple choice. The choice is as simple as that lottery versus the expected value of the lottery for certain. So I can easily give someone the choice, I can easily measure their preferences from that choice. Now I can show you how the class answered this question. Even before I see the answers, what I know is, generally speaking, this might not be true in every class, but generally speaking, the majority choice is choice 2. Most people would rather take the expected value of the lottery than the lottery itself. The second most popular is choice 1 generally, and then this is the least popular option where people say they are indifferent. So let's see what happened in this class. And this is what you see in this class, right? About 60% of people, they would rather choose the expected value over the lottery. And given the definition we are using, people who choose the expected value of the lottery over the lottery itself, now I know through this simple survey question that around 60% of people in this class, by this definition, are going to be classified as risk averse. About 27% of this class are going to be classified as risk loving, because they would rather take the lottery than the expected value for certain. And then 14%, which is oftentimes the least popular option, is going to be the number of people who are going to be risk neutral. Okay? So this simple definition is going to be the definition that economists use. And what that tells you is, even though intuitively we might have a different way of thinking about what risk aversion means, because you have seen people around you taking or not taking risks, being averse to or loving risks, and you might have some intuitive definition of what risk aversion means. But when it comes to economists, we do have a much simple, maybe too simplistic, it's possible, but we have a very simple definition of what it means to be risk averse. If you ever want to figure out if a friend of yours is risk averse or not, you give them a choice like that. You tell them, look, here are two options, here's a lottery, here's the expected value of the lottery for certain, which one do you really prefer more? And give me an honest answer. As long as they're giving you an honest answer, based on this definition, you have already put them in one of these three categories. They're either risk averse, risk loving, or risk neutral. And you should always remember the intuition is, the reason you give them that choice is because that choice guarantees that it's not that one of these two options is offering more money. They are both on average offering the same amount of money. For example, $5. It's just that one of them is being offered through risk, one of them is offered without any risk. And it's the preference between these two options which is revealing their attitudes towards risk. So that's going to be the second definition. The first definition we started with was the definition of certainty equivalence. This is going to be our definition of how we define risk attitudes. It's just a choice between any lottery and the expected value of the lottery. And then we'll have a third thing that we are going to define. So this is going to be risk attitudes. We defined certainty equivalent already. So certainty equivalent was defined on the last page. But I want to write it down again here. And before I write it down, I want one of you to try remembering what was the definition without looking into your notes. And someone try and tell us what was the definition of certainty equivalent we gave? This was based on another quiz question. Remember? So what was the definition? What is the certainty equivalent of a lottery? Give it a try.
It's the expected value.
No. Someone else? Go ahead.
It's the certain number that you're indifferent between lottery and.
Very nice. It's the, let me write it down. I want you folks to remember it. This is why I'm asking you this question. It's the amount of money that you receive for certain that makes you indifferent between, let's write it down, that's money and the lottery. That's the definition of certainty equivalent. We are going to use one more definition, and that's going to be the definition of risk premium. And risk premium is going to be defined as, we already have defined what certainty equivalent is, CE. So risk premium would just be EV of a lottery, so expected value of the lottery, minus the CE, certainty equivalent of the lottery. So these are the definitions that I would like you to remember from this class. The definition of risk attitudes, the definition of certainty equivalent and what it means, and also the definition of risk premium, which relies on the definition of certainty equivalent. If you don't understand the definition of CE or certainty equivalent, you would have a hard time understanding risk premium. Risk premium is the difference between those two. Risk premium is also something you might encounter later on in the life. But I want you to know the technical definition. Let me pause there. Are there any questions about just the definitions? How we categorize risk attitudes? Are there any questions about that? Are there any questions about the definition of a certainty equivalent of a lottery? Just to be clear, right, certainty equivalent of a lottery, we talked about it in this class, also in the previous class, and it was just this question, when we had asked you this question, that you could either get a lottery or you could get X dollars for certain, and what is the X that would make you indifferent to the lottery? That was the certainty equivalent for you. The amount of money, X, that you get for certain, that makes you indifferent to a lottery. So that was certainty equivalent. And then the third definition that we talked about, let me go back to my slides, is risk premium, which is the difference between the expected value and the certainty. Okay. So I want to talk about one more thing, which is kind of magical if you, yeah, go ahead.
Sorry, for the certainty equivalent, is it just a personal opinion or is there an equation to define?
How are those two different?
No, like is there an equation to find or is it just your personal preference?
Those two, what I mean to say is that those two things that you're saying
Yeah.
are not mutually exclusive,
Oh, okay.
right? It can be based on it is based on preferences, and in some cases it will have an equation, right? So it's not one or the other. For you, when I ask you the question, it's based on your preferences. If you told me your utility function, if you could give it to me, I could also figure it out based on an equation. But because I don't know your utility function, I just have to ask you as a survey question. Okay? But I want you to remember what this definition means, because this definition is what we are going to use if we ever have to write down an equation. It's going to come from this definition. Okay, we are going to see how that works, like the relationship between the definition and the equation supersede. But before we do that, I want to show you something that's really interesting and maybe it's not as obvious. We talked about risk attitudes and we said that we are going to classify people into these three bins. So risk averse would be the people who prefer the expected value over the lottery. Risk loving were the people who prefer lottery over expected value, and risk neutral were the people who are indifferent. It turns out that these categories that we have defined based on just that simple choice between a lottery and the expected value, it actually tells me a lot more about it. So let me get back to this distribution of how many people in this class are risk averse, risk loving, and risk neutral. This is what I got from the survey. Now I can't see what your utility function is. You might have a mathematical utility function that sits somewhere in the brain, and I can't see, through your skull into your brain and figure out what that utility function is. But what this theory tells me is that these 58% of people who have come out to be risk averse, based on the theory of risk preferences in economics, what it tells me is these 58% of people must also be people whose second derivative of utility is negative. Once again, I figured out if you're risk averse or risk neutral based on a simple choice. And I figured out 58% chose the expected value over the lottery. This theory says that anyone who is like that, there must also be people for whom, even though I can't really see what the utility function in their brain is, what I can say is that the second derivative of the utility function must be negative. It's kind of interesting that we can make that comment based on just that one choice. I can also make the exact opposite statement about risk-loving people. We had about these 27% of people who were risk-loving. What can I say about them? What I can say is that their second derivatives of their utility functions must be positive. And then for these 14% of people in class who said they were indifferent, based on this theory, they must have utility functions whose second derivative must be zero. Seems kind of magical that I can give you a choice and you can make a choice on that, and based on that I can have a hunch about how your utility function looks like. It's not exactly figuring out what exactly your utility function is, but it's telling me something about your utility function, and this is what it's telling me right now. The second derivative and the sign of the second derivative. Now, while that sinks in, let me try and explain what the second derivative really means. And to understand the second derivative of utility, I want to first understand the first derivative of utility. So think about a utility function, and in this chapter we think of utility functions as being a function of wealth. So suppose this is your utility. Okay? For that utility function, I want you to think about the interpretation of the first derivative of the utility function. So think about du dw. This is the first derivative. I'm just taking a derivative of u with respect to w. How should we interpret du dw in words? What should be the interpretation? In marginal terms, what does it mean?
Change of the utility with respect to
Yes. So the change in utility, so let's say how much extra utility do I get from $1 at the margin. Wherever you are, if I increase your wealth by 1 unit, and let's say the unit of wealth is dollars because we are in the USA, so then how much extra utility would I get if I got one more unit of wealth, which is one more dollar? That gives me the first derivative. That's the interpretation of the first derivative. So if I had to write it down in fewer words, I would just call this the marginal utility of $1. How much more dollar do I get? How much more utility do I get from that $1 more on the margin? Okay, that's the first derivative. Is it clear what the first derivative means? How we should interpret it? And you should see how this relates with our understanding of marginal revenue or marginal cost. The idea was always the same. If I increase the denominator by 1 unit, how much should I expect the numerator to increase by on the margin? That gives me the first derivative. Now what is the second derivative? The second derivative is just taking another derivative of the first derivative. This is just the definition of a second derivative. So I'm trying to see how does my marginal utility of $1 change when I increase width. That's the interpretation of the second derivative. So I want to write this down. This is saying, or this is asking, how does the marginal utility of $1 change as W increases, which also means that as I get richer. That's the interpretation of the second derivative. We didn't use any new concept here. This is just applying the concepts that we have always known. The idea of marginals. What should we expect? Should we expect the marginal utility of $1 to increase or decrease if I get richer? What do you think should happen? Decrease. So one way to think about it is, think about the marginal utility of $1 that is experienced by an unemployed person who doesn't have a lot of money. When you give them $1, they would feel quite happy because that would help them get maybe the next food groceries, because they really lack money. Now compare that to the exact extreme of Bill Gates. If you go and give Bill Gates $1 more, it doesn't really change the total amount of money they have. They have billions lying around. So the marginal utility of $1 more for Bill Gates is going to be close to zero. Whereas the marginal utility of this poorer person who doesn't have a job is going to be quite a bit higher. What does that tell you? As you get richer, you value that marginal dollar less. What would that mean? That would mean that as you get richer, the marginal utility decreases, and a decrease means that you would expect this sign to be zero. This is the expected sign of the second derivative of utility with respect to $1. Because you would expect that the marginal utility of $1 should keep decreasing, a negative slope, as you get richer and richer. And you can think of the example that I gave to help you see that. So that's the interpretation of the second derivative of utility. And under this theory, what it says is, maybe the reason that most people in these surveys, and think about this survey that I ran in this class, it's not just a survey that I ran in this class, I also ran it in the other section, and I've been running it for the last 8 years in every class that I've taught. And it's not just this class, most people choose, like in almost all classes, the most popular choice is choice 2, choosing the expected value over the lottery. So it tells you that there is an innate human tendency, if we could just extrapolate from the data that I've seen over the last 8 years, it seems to be a very consistent feature of human tendency to like the expected value of a lottery more than the lottery. It's very consistent, it happens every year across sections. And it does make sense given the fact that math says that risk-averse people should also have a negative second derivative. And negative second derivative is very intuitive because negative second derivative follows from the fact that people should generally have lower marginal utility of wealth as they get richer. Right, so I am now connecting concepts. There's a mathematical concept which connects how you choose between the expected value and the lottery and what your second derivative should be. This connection, I haven't proved it in class. The math is not that difficult, but it's still outside the scope of the class. But what I want to tell you is that the fact that most people prefer expected value over lottery is a pretty well-known fact, or at least it's pretty well established based on just the data that I have in this class and all the other classes I've taught so far. And it's connected to this mathematical equation which has got to do about the second derivative. And if you understood what the second derivative is, and if you haven't, you can ask questions. The second derivative, the expected sign is negative, which tells you that you would expect most people to have a negative sign on the second derivative. And that just makes sense because that's exactly what you see for risk-averse people who are also the major people in this class, the most common kind of people in this class, risk-averse people. Okay? Of course, this doesn't mean that it should always be negative, because there are people who are going to have a positive sign, and these are people who might also come across as being risk-loving. That's what this theory says, because this says that these two go hand in hand. Risk-loving behavior and positive sign on the second derivative. And then what other things go hand in hand? If you have 0 as your second derivative, then that goes hand in hand with you being indifferent, which is, I think, 14% of the class. Is option C, people who are indifferent. So I always find it interesting because the classification of risk attitudes is very simple. It's just a choice between a lottery and an expected value. I can ask you to do it, you can ask someone else to do it, you can easily classify them. And under this theory, as soon as you've classified them, you have somehow pinned down not their exact utility function, but the second derivative of it. And it tells you something about how their marginal utility of $1 changes as they become rich. Okay? So quick recap of what we have done so far. We've talked about definitions. We talked about the definition of certainty equivalence. We talked about the definition of risk premium. We also talked about how do we classify risk attitudes, these three kinds of people. And then what we did is, we also said that these risk attitudes are connected to the second derivatives. And we told you how they are. Now let's try and solve a math problem that's going to bring all of these concepts together at one time. So think about the following question. So think about this question. It's going to tell you that there is a person called Mary. They have a utility function. I'm going to give you the utility function. It's w raised to the power 1 over 3. I'm going to tell you that Mary has an initial wealth of 125,000. Let me highlight those two parts for now. So this is what I've talked about so far. It's a question on expected utility. So you do expect to see the exact utility function on the question, and also the initial wealth on the question, because we know that expected utility requires those two things to do anything with it. So that's why the utility function is given and the initial wealth is given. Then the question is going to ask you for what is your expected value, certainty equivalent, and risk premium for a lottery that could either raise her wealth by 35,000 or lower her wealth by 25,000 with equal probability, 50-50 chances. And this is going to help you apply some of the concepts that we have learned so far in class directly in a math problem. So before we start doing the whole problem, I want you to first think about, let's think about it a bit step by step. So I want you to could someone tell me whether Mary is risk averse, risk loving, or risk neutral given what is given on the question? That's my first question. You can solve it, but I also want you to think about if I had asked you, If Mary is risk averse, risk loving, or risk neutral, how would you have found it? What would be a way to go and find out that answer? You don't need to give me the answer, but you can tell me how would you have found it.
That's the secondary.
Yeah. So given we know that Marie's utility function is this, you could have got the second derivative, and that would have told you whether Marie is, or Mary is, risk loving, risk neutral, or risk averse. Let's do that quickly. So if I were to ask you to find out the first derivative, what would be the first derivative? 1/3 times w raised to the power of minus 2/3. Are there any questions about calculating that derivative? Is that clear? Now someone else, could you tell me what would be the second derivative? Correct?
-2/9
Yes.
and w with a -5.
Very nice. Thank you. That would be the second derivative. Now, what would be the sign of this second derivative? Negative. There's one argument that needs to be made when you say that. I can rewrite this as -2/9, 1 by w raised to the power 5/3. What guarantees that this term right over here is positive? Because I need that to be positive for the whole sign to be negative. What guarantees that that thing is positive?
Probably is bigger than zero.
That's right. We need to know that w is bigger than 0, wealth is greater than 0, and that is what guarantees that 1 by w raised to the power 5/3 is positive, and that would mean that the sign of the whole term is negative. And throughout this class, we are going to assume that wealth is positive, but you can't have negative wealth. So we are not going to think about cases where you have negative, for example. Okay, so that gives us the second derivative. This is negative. So what that would mean is the fact that this is negative, this whole thing, this would mean that Marie is risk averse. So I just wanted to quickly connect to that concept. What else is given on the question? What is given on the question other than this is that there is a lottery which can either raise her wealth to 35,000 or lower it by 35,000. So raise or lower by 35,000 with equal odds, 0.5. And I need to figure out expected value, certainty equivalent, and risk premium for it. Let's start with expected value. What is the expected value?
Zero.
Yes, very good. The expected value is 0. Now let's think about the certainty equivalent. And like one of you asked, is it a definition? Is it an equation? It is a definition, but it will lead to an equation, as you will see right now. So currently we have a definition of certainty equivalent. This is the amount of money for certain that makes you indifferent between getting that money versus getting the lottery. So how are we going to find it? We're going to say that, let's say that your certainty equivalent is some amount X. I don't know what that X is, but I'm in the business of finding out what that X is. If you are indifferent, given that this is the amount of money that makes you indifferent between the money and the lottery, what this should tell me is that the expected utility from, let me make this larger so it's easier to see, it must be that the expected utility from getting is certainty equivalent, which we have said is equal to X. This must be the same as the expected utility of getting the lottery. If you are indifferent between these two options, then it must be that you're indifferent because you get the same utility from those two cases. And we are not in the world of utility, we are in the world of expected utility. So it must be that you get the same expected utility from either getting the certainty equivalent, which we are assuming to be x, or getting the lottery. Yes?
Would you call the one where it's W is greater than zero? Shouldn't it be the other way? You have a bracket that says this is the first, isn't
This one?
it? Yeah.
W greater than 0? No, greater is that one. So if I want to write W greater than 0, I write it like this. Are you talking about this one?
That was one more.
This one is W greater than 0.
Yeah.
Would you rather have it this way? That would mean W less than 0. Wealth less than 0? No, so wealth is never less than 0 in this class. But if wealth was less than 0, you would be in a lot of trouble, because what it would mean is if wealth is negative, this term would be negative, so then the double derivative would be positive. Okay? The whole thing being negative comes from this negative side. It's only because W is greater than 0 that the whole thing is negative. If it wasn't, we would be in a bit.
Can you explain the expected utility in the CE equals X one more time?
We just assume that the CE is equal to x, that's all. Right? But are you asking about why this is true, or
Yeah, why that,
the whole equation holds?
no, why CE equals X is true.
Oh, we just assume that C is equal to x.
Okay.
Right? X is just an algebraic quantity, we have assumed that it's equal to x. Now let's figure out the expected utility on the left and right hand side. Let's start with the left hand side. So what is given is that this person has an initial wealth. And this initial wealth is equal to 125,000. So what would be your utility if you could get X dollars for certain? What would be your total utility in that case? What do you think it should be? Close. Like you have the right idea in your mind, but the idea is that you already have 125,000. You're going to get X dollars for certain on top of it. So your wealth is going to become this, where X is the CE. And then if that is your wealth that you end up with when you get X, then the utility you would end up getting is that raised to the power root. So you gave me the 1/3 root without the X in it, which is why it became 50, but it's 59. Okay. Can we pause there? Are there any questions about this? On the left hand side, you're getting X dollars for certain. On the right hand side, you're getting the lottery. If you're getting X dollars for certain, you started with some amount of wealth. You didn't start at 0. You started with 125,000. So once you get X dollars for certain on top of it, your wealth increases to 125,000 plus X. And then the utility becomes the 1/3 root of whatever that is. And then that's what you get on the left. Now, given that, can someone tell me what would I get on the right hand side? What would be the expected utility of getting the lottery on the right hand side? Think about what are the possible wealth you can get, and what would be the utility corresponding to that, and then we need to take expected utility. Lottery is something that either raises or lowers your wealth by 35,000. That is what is given on the question. So what are the two possible wealth levels you could be at? Yes. So the two possible wealth levels you could be at is 125,000 plus 35,000 or 125,000 minus 35,000, which would mean 160,000 and 90,000, as you said. So these are the possible wealth levels. We need to calculate expected utility. So first we need to calculate possible wealth levels. Then we calculate the corresponding utility on those cases. The corresponding utility would be the 1/3 root of those wealth levels. And then we need to take expected utility, which means the average of utility in those cases, which would mean that this case happens with probability 0.5, the other case happens with probability 0.5. So I need to multiply 0.5 with both of them and then I need to add them. Okay? I want you to understand how this right hand side works. How do we calculate expected utility? We first figure out what are the possible wealth levels you would end up with. When we do that, we need to take the initial wealth into account. Then for those corresponding wealth levels, I need to calculate the corresponding utility levels. I use the utility function to calculate that. And once I have that, I multiply it with the corresponding probabilities and that gives me expected. Are there any questions about that? Are the steps clear how we calculated the right hand side? First the wealth levels, then the utility levels, and then expected utility. Any questions? Okay, so then can someone tell me what you would get on the right hand side? Actually, let me ask you to solve the problem here on this, right? So, I want you to think about how you would solve it. Clearly, you would first need to get the right hand side. Then, okay, let's get there. Then, when gets the right hand side, you can tell me what you got as the right hand side. You might want to use a calculator. It's probably very easy for a calculator. Yeah?
49.5. 49.6.
Let's go one more decimal point. 49 points.
49.55.
55. Right? That would give me the right hand side. Now, what would be the next step if I want to solve for x? What should I do? Go ahead. Cube on both sides. Okay, very nice. So what I would like to do is, I would like to then say that 125,000 plus x has to be equal to 49.55 raised to the power 3. Whatever that is going to be, I need to figure that out. And once I figure that out, I can calculate x from there. It's not, it might not exactly match the answer. I just want you to get approximately what that is. And go till 2 decimal points or 2 points after the decimal and tell me what you get on the right hand side and what you get as x. Yes, one back. Yeah.
I got 125,000 plus X
Very good. 3,344 or something? Something like that sounds correct. So that's how you calculate the certainty equivalent. So my goal was to show you how to calculate it. My goal was to also answer the question of whether certainty equivalent is a definition or a formula. It's a definition that leads to a formula depending on that person's preferences. For this guy, the preferences was 1/3 power of the width. So we have to use their utility function to calculate this equation, which tells you that they are indifferent between getting the money for certain versus the water. And then we solve for it, and then we got the x. That gives us, there's one thing though, is x 3344 or is it minus 334? It's negative 334. Right. So the x you should get is a negative 1. So when we were to write down this answer, you'd get something like this, minus 334. There is a minus 3344, so that sounds like that. And then all that is left to do is to calculate the risk premium. The definition of the risk premium is it is equal to the expected value minus the certainty equivalent. Given we have both of them, you can just calculate the RP as the difference between those two. It is going to be this 3344, and that's the answer. Okay. So how do we calculate expected value? It's easy. How do we calculate certainty equivalent? We just did it. I want you to think about how we calculate these expected utilities. How do we calculate risk premium? It's the difference between the expected value and the certainty equivalent. If you got one of them, you got all of them. Any questions about how we solve this problem? Any questions about how we use the definition of certainty equivalent or how we use the definition of risk premium? Any questions about those things? Okay. Let me ask you another question then. So I want you to try this question. My Wi-Fi is not good. So without depending on the quiz currently, let me ask you this question. So let me give you two possible people. So let's say that there is one person whose utility function is w raised to the power 0.1. There's another person whose utility function is w raised to the power 0.5. Okay? These are the two people that I have in mind. And I want you to think about, can I tell who is risk averse? Or among these two people, are they both risk averse? Is one of them risk loving? Are any of them risk neutral? I want you to think about that question and give me an answer. This is going to be a bit more practice. Yes? That is correct. They are 0.1. Do you have an answer already?
Yeah, they're both.
Very good. So you could do the whole math, but you use a trick. So tell us the trick.
If you do a power rule, then you notice that the constant will become negative.
That's
You subtract.
That's right. So he used the trick. I'll give you what the trick is, and I think it's a good trick to remember generally. Is that if I give you a utility function, so I'm going to write down a general utility function. So let's say my utility function is w raised to the power alpha, where alpha is a constant. Okay. Alpha can be any constant. Alpha can be 0.1, 0.5. It turns out that there is a general result that says that if alpha is less than 1, in general between 0 and 1, you get a person who is risk averse. I'm just going to write it as RA. If alpha is exactly equal to 1, you get a person who is risk neutral. I'm going to write it as RN. And if you get alpha greater than 1, if that's the utility function of a person, or any alpha greater than 1, you always get someone who is risk low. And that is something we can generally write down. It follows pretty easily. I can show you how it follows. But before I show you how it follows, is this kind of formula clear? That whenever we have a utility function where w is raised to the power of some constant, let's say it's alpha, I can just look at what that constant is, and I would already know what would happen in terms of the risk attributes. Because whenever alpha is between 0 and 1, the double derivative would be negative. Whenever it's exactly equal to 1, the double derivative would be 0. Whenever it's greater than 1, the double derivative will be 1. That's the formula that you can remember. But I can also show you why this formula occurs. So think about this utility function and think about what its first derivative is. So du dw is just going to be alpha times w raised to the power alpha minus 1. So we all agree that would be the first derivative. Now think about the second derivative. The second derivative would be alpha times alpha minus 1 times w raised to the power alpha minus 2. Now that I've written it down, do we all agree that that would be the second derivative? Now with that in mind, now I want you to remember this wealth is positive. So this w raised to the power alpha minus 2, we don't need to worry about it. That's going to be positive. So all that really matters is the sign of this alpha times alpha minus 1. What's going on there? That's what really matters. Now think about someone for whom alpha lies between 0 and 1. If alpha lies between 0 and 1, this implies that alpha is positive. What about 1 minus alpha? Would 1 minus alpha be positive or negative if alpha lies between 0 and 1? Negative. Is that clear? Like think about it. If alpha is less than 1, then this. I have a typo. Let me fix that. If alpha is positive, and if alpha lies between 0 and 1, then this alpha minus 1 has to be negative because alpha itself is smaller. So what that tells me is, given alpha itself is positive and alpha minus 1 is negative in this range, I would get a second derivative which itself has to be negative. Is that clear? I made a typo there initially, now that I've fixed it, is it clear what I did there? If alpha is between 0 and 1, alpha being positive is obvious. If alpha is less than 1, alpha minus 1 would be negative. Is that part clear? And then the product of something that is positive and something that is negative itself must be negative. So that tells you that the second derivative has to be negative. And if it's negative, then these people must be risk averse. This is why we know that if alpha is between 0 and 1, people have to be risk averse. So the formula comes from somewhere that's pretty easy and accessible. You just take the second derivative and it tells you this. Think about what happens when alpha is exactly equal to 1. This term is going to vanish to 0 because we have an alpha minus 1 in here. So when alpha is equal to 1, the second derivative has to be exactly 0. And because the second derivative is going to be 0, that would give me that the portion is risk neutral. Because remember, the definition of risk neutral was the second derivative has to be 0. Right? Now the only thing that remains is alpha greater than 1. Think about what happens if alpha is greater than 1. Alpha is greater than 1 implies alpha itself is greater than 0. And it also implies that alpha minus 1 is greater than 0. Because alpha is greater than 0 and alpha minus 1 is also greater than 0, it means this second derivative has to be positive. And that would tell me that this portion has to be risk-liable because the second derivative is 1. So the fact that the range of alpha determines the risk attitudes, you can remember the formula, which is fine, or this rule, but I think you should also be able to figure it out if you ever forget it. You just take this second derivative and you just argue about what is the sign of alpha and alpha minus 1 in those ranges, and that really tells you what the sign of the second derivative is. Is that clear, folks? Is it clear what the science of alpha is? Now I can actually ask you another question based on what we have done so far. So let me ask you, it'll help if I draw a diagram first. So here is my diagram. This is still about risk attitudes. This is all possible alphas that you can think about. There is this cutoff point at exactly alpha equal to 1. What we do know is that exactly at this alpha equal to 1, I have risk neutral people. Anywhere to the left of it, we have risk averse people. Anywhere to the right of it, we have risk loving people. Right? This is what we got. For alpha greater than 1, we get risk loving. For alpha less than 1, we get risk averse. Alpha equal to 1 gives us risk neutral. The question that I've given you had these 2 points. They had alpha equal to 0.1, and we also had a guy who was alpha equal to 0.5. And as one of you answered, they are both risk averse. That's fine. Can we say something more? Can we say who among these two people is going to be more risk averse? Even though maybe all of us are risk averse, it is still possible that some of us are more risk averse than others. So even within risk averse people, you might be able to classify them. Now I haven't really told you how to classify them, but just going by intuition and going by this figure or diagram, can you make a guess, a hunch, of who among this alpha equal to 0.1 and alpha equal to 0.5 is more risk averse than the other? Who do you think is going to be the more risk averse person? 0.1. Right? What's the intuition that you used?
Because it's more towards the RNA size.
Exactly, right? The further away you are from risk neutrality, it would seem that maybe you get more and more risk averse. So that intuition is completely correct. So it is true that the further you go to the left, the more risk averse you are. This is the direction of more risk averse, going left. This is indeed right. We can formally define it in a few different ways. Like one way to define it would be whenever there is an opportunity to buy insurance, the alpha equal to 0.1 guy would be more ready to buy insurance. They would be willing to pay more than the other guy. That would be one way to define it. The particular way we are going to define it is the following. So on the slides, but let me just write it from scratch. There is something called the Arrow-Pratt measure. Arrow-Pratt measure of risk aversion. And this says that for any person, you can calculate the following fraction. What you would do is, on the numerator, you're going to calculate the second derivative of utility. On the denominator, you're going to calculate the first derivative of utility. And then I'm going to take a negative sign in front of it. This is called the Arrow-Pratt measure of risk aversion. And the higher this number is, the more risk averse you are going to be. Okay? This is the Arrow-Pratt measure of risk aversion, and the higher is the Arrow-Pratt measure of risk aversion, the more risk averse a person is. This comes from these two economists, Arrow and Pratt. Arrow is the more famous one out of those two. Arrow is Kenneth Arrow, who has the Nobel Prize in Economics and is probably the most influential microeconomist to have lived ever. And it's nice that we get to talk about at least one of his contributions in this class, because this is a class on intermediate micro. This is Arrow and Pratt's definition, or a way to measure who is more risk averse.
When you're talking about the higher number, are you talking about absolute value?
You wouldn't need to take an absolute value. So one of the homeworks that I want you to do is that, remember when we compared alpha equal to 0.1 and 0.5, and I said that intuitively who is more risk averse, and you said that intuitively it looks like 0.1 is more risk averse. As a homework, I want you to calculate the arrowcat measure of risk aversion for both of these guys, the alpha equal to 0.1 and the alpha equal to 0.5. And I want you to find the arrowcat index for both of them and show that your intuition really came from the right place, which is that it would indeed be the case that the 0.1 guy is more risk averse, because they are going to give you a higher arrowcat number than the other. Okay, that's going to be a problem. I will try and give you a reminder before the next class so that you can try it before the class. So that's going to be kind of the last thing we're going to talk about when it comes to risk attitudes. I think we've talked about most of the things. The next things we're going to do is we're going to talk about applications of risk preferences. We won't have enough time to start them today because they're going to take a little bit of time to cover, and I don't want to go half of it and leave the other half uncovered. But the next class we're going to talk about 3 applications of risk preferences, and the motivation would be, given we know that people are risk averse, 50% of this class is risk averse, how do firms use that to make money out of risk aversion? So that's going to be the topic of our next day's discussion. And that's going to be it for today.